Welcome to our speeches and Q&A session of this year's online competition. We are so excited to have all of you guys. Here today. This year's event is like special, obviously, with the conditions, the special conditions from this year. But we are really excited to present a seminar featuring 4 successful women in STEM. Our first 2 guest speakers, Dr. Sherry Gong, an accomplished and decorated American mathematician, and Dr. Doshi-Velez, an assistant professor in machine learning at Harvard University, will be giving talks about their journeys in STEM and how they became an assistant professor. And also assistant professor at University of California, Los Angeles, and Harvard University, respectively. And next, Mrs. Ying Liu will also talk about her career as an engineering director at Lyft and starting up her own company. And finally, Dr. Doblas will close out with a speech about her growth as the assistant professor in the electrical and computer engineering department at the University of Memphis. So welcome everyone, and we are so excited to get started.
Okay, hi everybody, I'm Amanda Joel. I am the Vice President of MIG, and we're so excited to have you here. Next, we will have the introduction of our MIG team. So Alex, if you would introduce yourself.
Hello, my name is Alex. I'm one of the problem writers this year for MIG, and I hope you guys really enjoyed the problems that you had on the test this year.
All right, next, can we have Sydney introduce herself?
Hi, I'm Sydney. I'm the treasurer for MIG.
All right, and then Marissa?
Hi, I'm Marissa, and I'm the director for MIG. I hope you enjoy our seminar.
All right, great. So now we can get started with speaker 1, Dr. Gong.
Thank you so much for inviting me. I'm delighted to be talking to you here today. I really hope you guys had fun with this contest. Okay, so I was asked to tell you a little bit about my journey so far in mathematics. So I will talk a little bit about how I got into mathematics, some of the things I like to think about. And also in the end, I'll tell you a little bit about some of the things I like to think about today. So I didn't always necessarily know I wanted to be a mathematician, but I think even since I was a child, I've always really liked mathematics. And what I really liked about math is the fact that you can use it to understand the world around us. So sometimes you can understand somehow really big things, even just with a little bit of mathematics. So for example, one of the math things I learned as a kid that I thought was really interesting was that you can use geometry to measure the radius of the Earth. This might have worked better for me since I actually grew up in Puerto Rico on an island, which is an island in the Caribbean. And so one of the things we did sort of as a school project was that we measured the radius of the Earth by looking at when the sun sets on the beach. So let me just sort of show you a little bit about how that works. I don't know if some of you might have seen this before, but so can people see my picture here? Okay, well.
Yeah, we can see it.
Okay. Yeah, so here what I'm illustrating is we're supposing that this big round thing in the middle here is the Earth, and it's rotating sort of in the direction that the arrow points. And then, so it's rotating this way. And then the sun, these yellow arrows, these orange arrows represent the sun's rays. And basically what you can do is you can lie down on the ground. So that's at the very top, you can see the person lying down. You can measure when the sun sets. Then you climb on top of one of these lifeguard towers and you measure when the sun sets again. And then you time the difference between these two sunsets. And you can see that the sun sets again once you've rotated a little bit farther along. right? So the guy who's standing on top of the box can like sees the sunset a little bit later, and then with that time difference and a little bit of um, like geometry, it turns out you can figure out what the radius of the Earth is, because in this case, like, it turns out that when the angle is very small, the angle between, like, the time between the first sunset and the second, the ratio of the height to the distance that the Earth has gone in that time is approximately 1/2 of the ratio of the distance, that same distance, to the radius of the Earth. And then you can figure out what the ratio of d to the radius of the Earth is by comparing it to the amount of time it went between sunsets. So that was something I found really interesting, because it's just like with a stopwatch, right? You can figure out what the radius of the Earth is, which, you know, you might like think would take actually a lot of work to figure out, and depending on sort of like how you want to think about it. So that was like some mathematics I learned at, you know, at a young age that I thought was really interesting. Another example of something I really liked, which, you know, became sort of relevant a couple of days ago, like with the lunar eclipses. But I'm not going to go into too much detail about how this works. But like, one thing I really liked learning as a kid is how lunar eclipses work. So, you know, there was a lunar eclipse a couple of days ago over Asia, and there's going to be one next month over most of the US, including where you guys live, but not including where I live. And like, when I was a kid, I learned that, you know, my parents, they're like, my dad is like from a village, and in the village where he grew up, whenever there was a lunar eclipse, people would go out and beat on their drums and generally make a lot of noise, because the idea is that the lunar eclipse is caused by this dog in the sky who's like eating up the moon, and you have to scare away the dog. And I think that's like a really cute explanation, because you're imagining some huge puppy just chomping on the moon. But I actually have always found the actual explanation for why lunar eclipses happen to be like sort of really interesting in its own right, when you think about it, because like it can explain things like why a lunar eclipse only happens on a full moon. Like, why can't you have a partial moon that happens to have a lunar eclipse, right? And also, you know, you can think about like why lunar eclipses only happen some months and not other months. So I don't know. It was just like, but it wasn't just that you can explain more. It was also that like it sort of, once you figure out why these things happen, everything just kind of clicks into place. Like you have all these different things and they all sort of click together. So anyway, then I got really into mathematics when I did Math Olympiad starting in high school. So first I was on the Puerto Rican team, and then on the US team after I moved to a boarding school. I went to a boarding school in the US. So like what I really liked about math contests is it's really the other people. Like you meet so many other people who are also interested in math. And I think that makes it just easier to be interested in math, because like, you know, interests and passion is often contagious. So it's just like really good to be around other people who are also interested in thinking about the world, interested in like solving problems, figuring things out, learning new things. So that's one of the things I really liked about math contests, is just the other people. Like people are trying to figure things out together, and I really liked that. So then when I went to college, I kicked around in a bunch of different subjects, which I highly recommend doing, but maybe not the way I did it. So I majored in math and with a minor in physics, and those were both subjects that I did contests in high school, like I did Math Olympiad and also Physics Olympiad. And I didn't actually learn about, I didn't actually sort of take that many classes in other subjects until pretty late in college. And I know it's pretty early for you guys to be thinking about what you plan to do in college, but I would recommend taking subjects that you like, that you hadn't really encountered before earlier on, because you never know, it might be something you're really interested in and actually want to major in. So for example, I didn't really take any classes in computer science or economics until like my last year of college. And at that point I was like, wow, this is really cool. I wish I'd actually taken classes in this earlier. So anyway, just small piece of advice. And then eventually after college, I went to graduate school where I didn't really know what I wanted to do specifically. So to choose the subfield that I worked in, which I'll tell you a little bit about, I basically like just asked around to the other graduate students and was just like, well, you like your advisor, what is he like to work with, or what is she like to work with? And I found, and like basically I just went by reviews, right? And figured out someone I wanted to work with, and then chose the specific subfield of mathematics I wanted to work in based on that. Just basically I chose the people I wanted to work with first and then the subject, which, you know, I think that worked reasonably well for me, like, because for me, like learning about mathematics, it's really much easier when there are other people who are like, when I like the other people who are interested in it. But I know that other people think about this differently. A lot of people are just, you know, they want to do whatever subject they personally are interested in and don't really care that much about what other people are doing. But I did the thing that I think probably worked for me, like, because I'm not really the kind of person who's just like specifically interested in something sort of in its own universe. And so, yeah, so, and that's like, so the subject I work in is called knot theory. It's the study of knots. So I guess I'll just end by telling you a little bit about knot theory and how it works. So this is something I didn't learn, no, I didn't know anything about when I started graduate school. So I started completely from scratch because, you know, when I went to graduate school, I didn't really choose a subject based on sort of what I was already interested in so much as like based on what I felt like, you know, what the cool professors were doing. And so, yeah, so let me just show you a picture again. So let me just tell you a little bit about knot theory. So knot theory is the study of knots. And a knot in mathematics is kind of like a knot you would see in real life, right? You take a string and you tie it up somehow. But the difference is that in knots, like in mathematics, it's after you tie up the string, you also glue the ends of the string together. So these are pictures, 3 pictures of knots that I'm showing you on the screen here. And like, so you can see it's kind of like you take a knot, you take a string, you tie it up, and then you glue the endpoints together. And one of the big questions in knot theory is sort of when are two such pictures, when do they actually represent the same knot? And when do they represent different knots? So for example, this first knot, it's called the trefoil. It's actually different from just like a circle, just like a straight up put a circle in space. And it's not actually very easy to see why it's not the same as the circle. So, you know, you could be like, well, this knot, like if you look at a picture of it, it crosses itself. And a circle, if you look at a picture of it, it doesn't have any crossings, right? It never goes over itself. But that's not really like, that doesn't really differentiate them because, for example, in this second picture, you have a knot that crosses over itself. But you can imagine that if you just sort of pulled this string down here up, you would end up getting just like a picture with like 1 crossing instead of 2. And then you can just sort of flip that little middle bit over and you get rid of that crossing as well. And so you see that this middle picture of a knot, I'm talking about 2-dimensional pictures, right? This middle picture of a knot, it is actually just like the completely undone, just a circle. Like it's the same as if you didn't actually tie a knot. You just took your string and glued the ends together, right? So like, I guess one of the things, you know, you might be interested in is the question of like, how do you know that this middle one is actually what's called the unknot? So that's just, you take a string, don't tie anything into it, and glue the ends together. But the one on the left is not the unknot. And so like here, just to give another example, I have this third picture, which looks like it has 4 crossings. So meaning like when you draw it on when you draw a picture of it, it crosses itself 4 times. But like, if you think about it, you could actually just, if you just flip this arc, this piece of the string, if you just sort of flip it over so that it's on this side, you can actually just, you can replace these 2 crossings with a single crossing. And it turns out that if you look at what happens when you do that, it's not that hard to see that this knot is actually the same as the first knot. So, so like, the question you can ask is like, how do you know when 2 knots are the same, and how do you know when they're not the same? So like, when 2 knots are the same, if you want to show someone that 2 knots are the same, it's generally not that hard, because you just do what I just showed you, right? What I just said to you is you should say, okay, well, if I just flip this arc over, then it becomes this one. Or in this case, if I just pull this arc up and then flip over here, then it becomes just the circle. So like that side, if you want to show that 2 knots are actually the same, it's just a matter of describing how you get from one to the other. But how do you show that 2 knots aren't the same? That's like a much deeper question. And there are various ways to do it. One of them is called like, well, actually, really, there's only one way to do it, but there's various flavors of this one way. And that way is called using an invariant. And what that means is you want to assign a quantity, could be a number, could be a polynomial, just something. You want to assign this thing to each of your knots in such a way that you can show that if 2 knots are actually the same, in the sense that you can just sort of deform one of them to the other, like I've described here, you know, flipping the arcs, twisting things, etc. Then they would give you the same invariant. So like, there's one of the most basic ones is called the Jones polynomial, which means, which I'm not going to tell you exactly what it does because it's a little bit technical, but basically it's, you take each knot and it assigns it to it like a polynomial, like, you know, x squared plus 1 or like x squared plus 1 plus x. So in this, for that case, this unknot, like this middle one, which is really just the circle, it would get assigned basically 1, and this knot down here would get assigned x squared plus x plus 1, something like that. And then you can see that these 2 knots are not the same because they have different polynomials, and you can show that if 2 knots are the same, like you can transform one to the other, then each of these transformation steps sort of preserves the polynomial. It gives you, so they'll give you the same polynomial. So the specific kind of invariant that I like to work with is not the Jones polynomial. It's something that has a little bit more to do with physics. So the idea is that if you think about a knot, you can think about it here. I'm drawing pictures in 2 dimensions. So I'm drawing pictures like on the plane because that's, you know, because I can't draw in 3 dimensions. But what you want to do is think about the knot in 3 dimensions. And then you want to consider like, basically, you want to think about a space that has like something like called a singularity at the knot, which means that like the space is somehow twisted at the knot. And then what you want to do is think about like, you know, electromagnetic fields. So that's like, you know, if you have magnets, then like all of space around the magnet is somehow has what's called like a magnetic field, which basically means if you put another magnet, it can feel the presence of this magnet, even though it's not actually there, right? And that's because this magnet is exerting what's called an electromagnetic field on space. So what you want to do is basically you think about this twisted space, and then you think about all possible electromagnetic fields, that you can get on this space, and that's going to be an infinite dimensional space. And then doing some analysis on this infinite dimensional space, you can actually extract information about the knot. And that's the kind of math I do. It's basically like, it's like saying you have this knot in three-dimensional space. So that's like a three-dimensional world, which basically has physics. And then if two knots are the same, actually the same knot, then there's basically supposed to give you the same physics. And by basically doing physics, like this, detecting what physics is, there are, wow, that's not really making a lot of sense, but basically it's sort of what I'm saying is like like by detecting the kinds of worlds you can get on these three-dimensional spaces, you can end up figuring out information about the knot. So that's basically an overview of the kind of mathematics that that I think about, and sort of what, like, how I got where I am in math, and so far. So yeah, okay, cool. That's, I guess, what I wanted to tell you about. Thanks for listening.
All right, thank you so much, Dr. Sherry.
It is my great pleasure to introduce Dr. Finale Doshi-Velez, our second speaker of today's seminar. Dr. Doshi-Velez is the Assistant Professor of Computer Science and the head of the Data to Actionable Knowledge Group at Harvard Paulson School of Engineering and Applied Sciences. She completed her master's degree from the University of Cambridge as a Marshall Scholar, her PhD from Massachusetts Institute of Technology, and her postdoc at Harvard Medical School. Dr. Doshi-Velez's interests include machine learning, healthcare, and interpretability. Please join me in welcoming Dr. Doshi-Velez.
Hi, thanks everyone for having me, and sorry I was just like a few minutes late joining onto the call. As one thing you'll hear from my story is that I feel like being a girl in math or a girl in STEM wasn't so hard until I became like a mom in STEM. And just trying to juggle everything is definitely a set of challenges that I had not expected. But maybe a little bit about myself before I tell you a little bit about my story. And I want to open up for questions, and I'm happy to make it a joint Q&A or however we want to do it. My research these days has to do with mostly applications for healthcare. What I do in my lab is we build probabilistic models of how patients may respond to treatments given loads of data. So we get a big hospital database and we look at what treatments patients got, what sort of responses happened, and these databases are extremely messy. So you have to do a lot of reasoning under uncertainty, a lot of statistics to build up these models. And then once we have these models, we can recommend what might be useful actions for a particular patient rather than just on average. And that's really the goal. But as I mentioned, because these data are just so messy, and our recommendation is just one thing that might be part of a very large hospital workflow. And maybe people are doing something not because it's like the optimal action now, but overall in the scheme of things, in the way the hospital runs things, there are certain actions that are kind of beneficial because they set up for other opportunities, allow nurses to get to other patients faster. You know, there may be lots of different considerations that go into treatment decisions. A really important part of my work as well is how do you make all of this machine learning, AI, statistics interpretable and accessible to clinicians so that they can vet the decisions, see if they make sense, and incorporate them into their workflow. And for me, this is really exciting. When I was in middle and high school, I just never conceived that this is stuff that you do with math. The things that I was, I thought geometry was fun. I loved linear algebra. Calculus was a blast. Like all of these things are super fun, but they never seem connected to the real world. And one thing that's really exciting for me now is just how I'm able to take all of these things that I think are super fun day to day, dealing with probability, dealing with statistics, and connect it to problems that really matter. So that's what I'm doing. It definitely took, some circuitous path to, exactly get there. But for all of you who are thinking about, oh, what could I do with this passion that I have for math? There's loads and loads of stuff, as you're hearing from all the speakers. that you can do. And it's an incredible tool that you can apply to just about any problem that you're interested in solving. So that's what I'm doing now. But then I also wanted to share a little bit about how I got there and maybe some takeaways that I've learned along the way. And then again, I'm happy to take questions because you all know what you want to know better than I do. So in terms of how I got here, I feel quite lucky. I grew up in a family that was extremely supportive of math and pro education more generally. Math was not a girl thing. It was not a boy thing. It was just like a survival thing. It was just like a thing you did every day. Like if you're running a business, you got to know how to balance the books. If you're inviting loads of people over to a party and you want to make some bhajiyas, you got to know like how many potatoes you're going to need to make how many bhajiyas for how many people. There was this like kind of a very everyday, like numbers were just kind of like an expected part of your life. The way that my parents would keep us occupied in the grocery store would have us keep tally of how much everything costs and see if it added up to what it actually cost at the register. So I feel incredibly lucky to be have grown up in a family where math was not like a passion or a thing. It was just like, it was normal, right? This is just what you did all the time. And going forward, my parents really helped advocate for me going to various math contests or STEM things or just education in general. So overall, I feel like incredibly, incredibly lucky, both to my parents and to all the great teachers that I've had along the way, that I just had a really awesome experience with math and with STEM more broadly. That said, I think one thing that I definitely learned is that I did observe how different women in math, different girls in math and STEM kind of got treated along the way. And I think one thing that really helped me is that when I was in a math situation, when I was in a STEM situation like robotics, I tended to stay very technical. I like, you want to build a robot, I want to build a robot. We're all here to build robots. And I think that helped me. And I think it's a contentious sort of thing, right? Because you might think like, do I have to hide a part of myself? Like, can I be a girl and a roboticist? Can I be a this and a that? And I think it's very complicated. And so, but one thing that did help me is that I really focused on that commonality, that if we're in a situation where we're trying to work out math together and the conversation got sidetracked to something else, kind of bring it back to math. If you're working on a robot, you brought the conversation back to robots, to the tools that you were building, to the problem at hand, and finding ways to really emphasize the commonality between what I was passionate about and what everyone else in the room, whatever gender they were, was passionate about, was definitely something that I didn't realize I was doing at the time, but as I look back, I think was really beneficial for me in terms of navigating my peers. Again, I was very lucky to have extremely supportive parents and teachers. So that's one thing. So as I said, overall life was really good. After that, I went to college, I went to grad school. And then I get to the point where I'm finishing up my PhD. And that's when I had my first child. And I feel like this is where things changed a lot. And in terms of the challenges that I faced, because and these challenges largely came down to time. That I feel like we live in a society where we're getting more and more supportive of women in the workplace. Not that there isn't work to be done, but when I talk to women of previous generations and what it was like, they're talking about, there were no bathrooms in this building, or women's bathrooms in this building, or really extreme like situations of, really overt situations of sexism in the workplace that I have been very fortunate, again, not to have experienced those sorts of things. And I'm not saying that that doesn't happen today, but I feel like we have made great progress. And for me, the biggest challenge came when I became a caretaker. I became a mom, in addition to the work that I had. and in this setting, we have, again, I think we've made great strides in terms of women in the workplace, but we've kind of made those strides by kind of letting the women do everything that the men do, which includes, working the long hours, and, going for all the things that the men do, which is great, right? Until you have two working parents, and both your workplaces expect you to, if you want to have, a fancy job, are expecting you to put in a ton of hours into your work, or at least a substantial number of hours into your work. And you're also trying to figure out how you balance a family with all of that. And things are, what I've noticed in the situation is that, again, like, people are very understanding. If I say that I need to leave at a certain time to go pick up my kids, no one questions. And yet I was having a Zoom call with one of my colleagues, a male colleague, and it was kind of interesting because he said, I've noticed something this week. He said, or over this period of pandemic, he was like, when I have conversations with my male colleagues on Zoom, I very rarely see, them, being tackled by their children. But when I have, phone calls with my female colleagues with young children, they're constantly being interrupted by their kids. They're clearly trying to juggle these two things at the same time while being at home. And he was like, yeah, I don't think I really realized that there was this difference until now. And it's like, well, yes, it does kind of exist. And so I think that's what I feel like is the major challenge for my generation, for your generation, like figuring out like how do we think about women in STEM is one question, but I think a closely related question, just because women end up doing a lot more caretaking, is how are you a caretaker in STEM? Again, where many of these jobs are kind of, on one hand, very flexible, right? You can work from home, you can write software at any time of day, and that ends up being a somewhat mixed blessing, because it can mean that, yes, you can pick up your kids, you can make them dinner, you can put them into bed, and then you feel the expectation to like log back in again and start working again. And as we go forward, I think that the solution may come from demanding more for women, but it may also come from helping educate the men around us, educate, encourage, and support the men around us in care support, in caretaking roles, because we're not gonna, the math just doesn't add up, right? If you just want to have, say both partners having full-time jobs and wanting to be really engaged with their families, it can be really hard. So that is, for me, what has been personally, again, I want to really emphasize personally, the biggest challenge I feel of being a woman in STEM, and it's probably just relates in general to being a working woman and a mom in general. Again, I feel very lucky that I haven't had to deal with a lot of other issues that a lot of other women have faced, and those are also super, super important. But here's one that I think is a challenge that at some point we're going to have to figure out how we're going to do this, because again, otherwise the numbers are just not going to add up. So at this point, I would love to like open it up for questions from people. I mean, I can chat more about some of my research and some more of my journey, but I think it's great to hear from you all and hear about what you'd like me to chat about. It can be research related to the healthcare problems, or overcoming challenges, whatever is interesting to you.
Hi, I guess I can start off, and anybody else who has questions can ask them in the comments section. You mentioned working in a hospital and managing data from the hospital. My aunt actually runs a hospital in China, and I have also been like sorting out some of the data for her using like different tools. Can you elaborate more on your experience about that?
Yeah, I think that there's a ton of really exciting stuff that we can do in that space. So there's two major areas that I tend to think about when I think about hospitals and data. One is operational and one is more clinical. And I think the operational side is kind of like, how can you schedule surgeries so that if you know roughly how long different surgeries are going to take, you can put them into a day and use your time more efficiently. If you know how long people are going to need ICU beds or who are likely going to need ICU beds, you can use that to shuffle flow through a hospital. So I think there's a lot of those sorts of things that one can do. And I think those are great because they give an immediate benefit. It usually streamlining care means more people get care, but the stakes are not super high. And then another set of questions relate to the clinical aspect. So like, which treatments are working for which patients. And I think there one has to be very, very careful. Not that you don't have to be careful with operational questions as well, because the stakes are much higher. If you make recommendations that are incorrect, you can run into a lot of trouble, right? These are sick people already, and you're doing things that may affect their lives significantly. And so in that context, it's really important also to remember that the data are biased. Let me give you just like an example of something that happens like in ICU units we've seen, where we were trying to make certain predictions about like which treatments are going to work for which patients. We've came up with something that looked like a flow of like, okay, patients who look like this, if you give them this vasopressor treatment, it seems to benefit, and patients who look slightly different, you give them this treatment, it's actually detrimental, right? You shouldn't give them this treatment. And then we showed it to the clinicians, and they were like, well, in a way, this is not telling us anything, because the patients who got worse, these are patients who were much sicker anyway. And there were things that were kind of subtle in the data that you wouldn't, but were much harder to pick up, where they were like, oh, I know exactly what this like one value means. I mean, that means that this patient must be under consideration for this other disease that's not coded in the data set, or, I bet this is what's going on. So I think that's something that's really important to be cognizant of. Maybe the most important thing I would say is like talking to people, finding the real problem that you can solve. So if your aunt operates stuff, then she probably knows. People on her team probably know what might be useful. So I'm looking down at the comments. So the first question is, am I doing any research related to COVID-19? I would love to be, but right now, as I mentioned, I'm juggling homeschooling and my work and caretaking in general. So I am mostly just keeping track with the project collaborations that I have, but there's a lot of really great work being done on COVID-19 now, computational work. So I really salute the people who are doing that work. I think it's super important work that I've been doing. The next question is, when do you expect AI doctors replacing traditional office visits? I don't, period. And that's because, so what my vision really is in terms of AI and doctors is that AIs and doctors have very different skills. So the things that the AI can do that the doctor cannot do is that the AI can go back and look at past data about that patient, and can also compare that past data to other patients in the database, do analysis. And doctors are super squeezed for time. If they can see your current records, that is a win. They're certainly not going to have time to like dig through all the details of your past records before, like as you're chatting with them, right? So what the AI can do, the superpower of the AI, is to look at all of these data from the past. But these data are pretty crappy data. The doctor, on the other hand, sitting in front of you, they can ask you all sorts of questions. They can say, what do you mean like you have insomnia, right? There might be a flag that says insomnia in your record, but there's so many variations, for example, of insomnia. Tell me more, like, when does it happen? How does it happen? Are there any triggers? And they can get deep information rather than broad information about the patient. So what I'm really excited about is how we can put those two together to be able to solve problems. I think there's some things like problems in radiology and pathology that can be somewhat automated, but I think a lot of stuff is still going to require a teamwork of doctors and clinicians. I'm going to look at the next one. So the next question is, did you ever doubt yourself while building your career? And if so, how did you get it back on track? So I mean, I think I don't know, everyone, lots of people have their inner imposter syndrome. I certainly do. One of the most like cathartic events that I went to in grad school was a talk on the imposter syndrome, and the talk itself was fine, but what was most amazing about that talk was like 400 people showed up. And so the kind of like the absurdity of like, 400 people think you're only one person who, like somehow just like slipped through the cracks and is really bad, but everyone thinks they're good and somehow they're going to be found out. You just helped highlight the fact that, hey, like everyone has insecurities and these sorts of things. So I think it's just something that, at least for me, like I've learned to live with, I've learned to laugh about. And I guess I count the things I get done. And that really helps me. Like if I think about all the things that I want to get to that I don't get to, that's really hard because there's always more research you want to do. There's always more parenting that you want to do. There's always more hobbies that you want to do, and you just feel like a complete failure. But if you look back and you're like, hey, like I helped edit that paper today. I helped run this, we ran this simulation today. In the past X months, I've had these papers published. I got this grant. And if you just look back and you think about the things that you have accomplished, I find that super helpful in terms of remembering kind of where things are. And then as you look to the future, I mean, especially as we've all been home, I did a serious restructuring of like, okay, if I have about 4 hours in my workday, how can I keep, how do I optimize this to keep my career on track, with 4 hours of work a day or something like that? What can I cut? And I was very ruthless about what I cut in these last couple months. For me, like, yes, I'm always doubting, how I'm going to be able to do things. But I think it helps, like being a person in STEM, like I think we're there, like we have the skills, we're logical thinkers. We're problem solvers, we're puzzlers. And so when I find myself in that situation, I try to turn it back into a puzzle, a problem, think about how I can put the pieces together. Great. So the next question is, what do you think about the personalization of healthcare? Is it the future mainstream of healthcare? I sure hope so. Our current healthcare, a lot of the recommendations are based off of very small clinical trials of and often of populations that don't match the person that the thing is being, the treatment is being applied to. We just have general, like, your blood pressure should be in this range, or like your BMI should be in this range. When I was having kids, it was like your baby's like head to abdominal ratio should be in this range, and none of those ranges were calibrated for me or anyone who really looked like me. A lot of these are studies of middle-aged white men even being applied to women, and in some cases, if you're lucky, it's middle-aged white women, Northern European women being applied to me. And so I think one thing that AI can help us do is really help if we look at everyone who's being treated and what the treatment responses are, I don't think it's going to be personalized to just to me, but if you can even, stratify to my group and figure out what is my group, right? Is it like people of Indian descent? Are all Southeast Asians the same for a particular bit of calculation that you need to do with physiology? Who knows, right? And AI can help us figure out both like how big the bins need to be for treatment personalization, and also what might need to happen in each of those bins. All right. Cool. Okay, so 2 more questions, and then we need to stop. I'm seeing from the chat. When you were little, who did you look up to? Gosh, that there's like a lot of there's a lot of people. So one story that I've told before, but not to you all, is that I guess I felt a lot of tension. Like I grew up in a family that was very much into Gandhi and Mother Teresa and people who did social work and brought about social change and governmental change. But people who were clearly like people. And it was hard for me because like I was interested in STEM, and I didn't know how to connect the fact that I wanted to somehow be out there like doing good in the world, and I liked numbers. I think this relates to the second question as well. Like, when did you want to work in the field of healthcare and why? So for a while, I just felt guilty about this whole thing. I felt like I should be like out there, like volunteering, out there, like creating social change. And kind of what I wanted to do was like trigonometry problems. Like it was just way more exciting for me. And then undergrad, I actually did aerospace engineering. And throughout that time, these two things are very different, distinct. Like I did some educational outreach and enrichment and teaching and those sorts of things. And then I did my research. And then toward the end of my PhD was when I finally was like, you know what, I need to bring these strands together. I want to figure out how I can be like doing the math I love to further things that I really care about. And I talked to like, must have been close to 40 people toward the end of my PhD in areas that I cared about. So I talked to people in healthcare, I talked to people in education, I talked to people in energy conservation and in climate, with the goal of being like, hey, like I just think these causes are super important, and I want to do math. Like, can me doing math like help you in any way? And many times the answer was no, right? Because even if you think about healthcare, you think a lot about social change, the most immediate changes are going to come from regulation and legislative action, right? Like there's structural things that need to happen to make immediate changes on these really, really big problems. And so then I found this middle ground of like, well, okay, I'm not here, that there is that large set of changes that need to happen, and I can support those causes. But there's longer term vision here, right? Like where the AI could be useful, right? Like this question of stratifying for a particular, like what are the right groups to stratify on, right? Like who are the people who go into a category for a particular problem, and how should you treat them? And this is not the most immediate problem when loads of people don't even have access to sufficient healthcare, and there's all sorts of biases in healthcare, right? So I fully acknowledge that. And yet it's the middle ground that I found between being able to do things that I'm really passionate about day to day, and feel like I'm making a positive difference on issues that I care about. So that's always been my tension. And maybe to end, like for those of you who feel that way, that you're pulled in different directions, there may be ways to bring this together. Like I mentioned at the beginning, when I was in high school and middle school, I never thought that math could be used for all this sort of stuff. But it's also okay to be excited about multiple things, that you don't have to be just a girl in STEM or a woman in STEM. You can be a woman in STEM and a supporter of, an advocate for various types of social causes. And you can be a parent, and you can be so many different things. And like maybe the most important word to leave with is like, and that we can be all of these different things. And we don't need to be in just one bucket in terms of how we view ourselves.
All right, thank you, Mrs. Doshi-Velez. Thank you so much for the wonderful insight, whether it relates to your career or in medicine, or in just life advice in general. So we really appreciate you coming to speak at our competition today.
Thank you for having me.
Thank you. Now let's take it back to Miss Liu for another Q&A. Thank you so much for your patience. And I will hand it over to Amanda for some questions.
Hi, all right. So our first question would be, when did your interest in the STEM-related field begin?
So actually, I just listened to what Dr. Doshi was talking about. I strongly echo something she mentioned about like interest in math. Right? It's not a girl thing, it's not a boy thing. It's a survival thing. I felt like when I grew up, that's what I experienced as well. I never thought about whether girls should be good at particular things and guys should be good at other things. And I'm really glad I wasn't too sophisticated to think about those things. To me at that time is, hey, I find I'm good at this and I want to get better at it. Right. So if I had thought more about this, I probably would get myself more confused. So I think I was lucky in that sense of, just focus on what I really want to do and get better. So to answer your question, when did I find, I'm interested in this? I think it's a positive feedback loop. Is that first I was good at it, and then I felt I want to get better at it. So it's just that thing keep on going. So there wasn't a particular moment or something that made me think this way.
All right, I see. So what drives you in your STEM career?
What drives me into STEM career? So one thing is, I find I'm good at math. It's really interesting because in primary school, I did remember my teacher was saying, oh, if in the future you want to have a career or you want to have a job, you better get at math, physics, or chemistry. Those are the three things that will land you a job in the future. So that got me going about doing more about the math. And once I get into this field, and in college I was in the engineering school in Tsinghua, the top engineering school in China, and there's so few women in there. I guess that's the moment where I started thinking about, hey, there was a little bit gender issue in there, and why there's so many, girls, so few of us in there. So what drives me into this, I think it's just, I want to get better at certain things. And that's probably the most motivating factor. Another thing I would point it out is just how fun this whole, I actually started interacting with computer in high school and college. Something particularly attracted me is how fast you can get your feedback from doing a little programming, right? So you program something and in seconds you get or sometimes milliseconds, right? You can get your result back and then you can improve from there. This is very different from the traditional education that we're having, where you spend hours working on something and then it take a month or so, you take an exam and find out, oh, you're actually not doing so well, you need to improve. So to me, that cycle is too long. So I really enjoyed programming where, I in there in seconds, I can get the feedback and then I can improve. So that really got me.
Great, thank you. So we have a question from one of the students. She says, "Do people ever doubt you or underestimate your ability because of your gender?"
I'm sure that happened many times. Once I started a career in computer science, I think in a very long time, I was always the only woman, either in the engineering team or later I become a manager and sitting some of the staff meeting. I was the only woman in there. So if there's people having special, doubt or underestimate the ability, but they never show. And I wasn't thinking it too much or more focused on, what is the agenda I want to drive? What is the issue I want to solve in there? I think that really helped me to stay focused.
Right, right, I see. All right, so what is the most important role of STEM in the world today from your perspective?
Hmm. The most important role of STEM. I think I have a bias in here just because I spent so much time in computer science and especially in the field of AI. Um, I could definitely see how AI is shaping the future. Actually, it's already doing a lot of things today. It's just without explicit knowledge of it. Right. So if you think about all the things that you read, on Twitter, on Facebook, it's recommended to you from an AI system. Right. And so the news you read, the books that you shop on Amazon, the things that you hear from podcasts, and some of the things that you interact every day, right? So you have smart home devices. You talk to Alexa. Um, you know, many of this is actually there's a AI system behind it, and they're trying to do the best personalization service to you, based on your past experience, the books you bought, right, the kind of things that you search on, that we recommend. So it is shaping our world and our life, and it's kind of influencing how we think about things. So one thing is really tricky right now is people think about, does AI box ourselves into our echo chamber, right? So you see what you want to see, and they recommend a lot more of that to you. So one research area, and this is how do we break out of those, right? Introduce more diversity, into the daily topics that we interact with.
Yes, I think math and STEM definitely does touch a lot more aspects in our lives than we usually realize. So we
Mm-hmm.
also have a question from Brianna in the chat. She asks, when do you expect people to be able to use self-driving cars on a basis?
Okay. Very good question. So years ago, people were telling you that in 2019, 2020 is a magic year, right? But that didn't happen last year, and it's very hard to imagine it happens this year. I think the whole industry become a lot more mature about thinking of self-driving. So the general answer that I have is in decades, and my answer is roughly around that time, and there's specific reason for that. So after spending couple years in self-driving, and especially about 7, 8 years in AI field, right? You know what AI can do, and you see the clear limitations of AI. So in the sense of building self-driving car, and AI is a big part of it, right? It's essentially that brain inside the car that, the sensors are there to collect the signal. It's the brain that may think, what you can see, form into vision. So there's technical barriers that there today that's limiting us from fully deploying all the cameras and let the AI system to tell you what they see. You still need a human to be in there. So there's technical barrier, and the best estimation is a lot of the some of the elements in there is still in open research. So when things are in open research, right? So we know that it cannot be used in real world application yet. So if I have to estimate what is the breakthrough of that open research, I just roughly say 5 years. So let's say 5 years, there's a breakthrough. There's a new AI algorithm that can make us see better, and especially on the planning side, plan better about motion. And then it will take another, at least 5 years to grind it down all this, research ideas, right, or research breakthroughs into an engineering solution. And that solves how many nines, right? 99.9999% of the problems, so that you can feel more confident sitting in a car without a driver. So in that case, that's a 5 year plus 5 years, so at least a decade from now. So that's my long answer to this.
All right, thank you so much. We also have a question about what is your favorite math subject?
That was too long ago. I don't remember the math courses that I took, but favorite math. But just in general, I do find myself thinking in pictures. So when I was taking math classes, right? So linear algebra, this was one course I don't even know how to say it in English. Probably it's called 空间几何 in Chinese. Probably called geometry or something in English. That's where I find I'm really particularly good at it, just by looking at how these things are, laid out in 2D. I can picture them in 3D. So that's something I know, I know I'm good, and I certainly find it fascinating to do a lot more in there. Okay.
All right, so our next question is, what is one of your proudest accomplishments in your career regarding the fields of STEM?
So my career is about engineering, and engineers are general builders and makers, right? So making things happen. One of my favorite stories is redesigning the product of reCAPTCHA. So, oh, thanks. Somebody mentioned about it's spatial geometry. Now I learned something. So I actually have a couple of slides just to talk about what that is, because many of people today don't encounter this product anymore. But this is kind of what the internet looked like a couple of years ago. So let me present. Let me see if I can do this. Share my screen. And yeah. All right. Can you see my screen?
Yes.
Okay. So this is the product I worked on years ago. So this is called reCAPTCHA. So what it does is a lot of websites, right? They want to prevent the bots to go spam and abuse their services. So they put some challenges like this, where they ask you to transcribe, the text, so that you can prove to the website that you're a human, not a robot. And this is viable because in the early days, computer vision wasn't that advanced. So just by slightly distort some text, you can tell that a human can solve this, but bots cannot. Well, fortunately or unfortunately, computer vision has improved, especially on OCR, it's optical character recognition. They're getting much better at recognizing this distortions. So we have to distort it a lot more until it looks like something on the right-hand side, where this kind of distortion, when we present it to human, only 33% of them can transcribe it. I myself honestly have a hard time transcribing this. So this is what product looked like in late 2012 when I took over that team. And we did this experiment with human, right? Find out extremely hard. So that's also the time when Google Brain published a paper and saying that, we feed millions of YouTube videos into Google Brain. And so Google Brain can, without explicitly telling it, actually can recognize the concept of cats and dogs. So we're applying the same technology in here, and we feed a Google Brain system with lots of distortions we have. And we are able to build a system that can solve our CAPTCHA at 99.8%. So earlier I was saying human is 33%, and computers at that time, machine learning can do 99.8. So that's the time we know that this technology is totally obsolete. We cannot use this to tell human bots apart. Probably more than often we find out who can solve it is more likely a bot, right? So then me and my team work with a large group of people, communities inside Google, especially usability group and security groups together. We redesigned the product to look like this. So you probably still encounter this sometimes in some websites, where it gives you a checkbox. You click on it, and we can tell you whether you're bots, you're a robot, or you're a human. So what behind the scene happens is, we do a pre-classification based on the various signals that we know about you, right? So if we're confident that you're human, we let you pass through directly. If we're confident that you're a bot because you visit our server a million times a day, we directly reject you. But in between, we still give you some kind of challenge. And as I mentioned earlier, the text distortion is obsolete, but there's still a lot of difficult challenges for computer vision at doing 2014, 2015-ish. So let me go back. So we'll give you challenges like this. Right? The first one looked like, it's called image classification, where it gives you 9 pictures and say, oh, how many of them has a house in there? Right? The second type of question is even harder for computer vision at that time, is giving you a picture, ask you to localize where explicitly that object is, because we know there's street signs. We want you to pick the tiles that contain them. And if we ask the same question to enough people and we shift the picture a little bit, we actually can get a very accurate contour of the object itself. Right. So that's the product I was running, and we relaunched the product as this I'm Not a Robot solution. And we launched it in 2014. In 2015, this won the FCC award of one of the most innovative product in the over the internet, and especially for its contribution to solve the problem for people with accessibility needs. Because for most of them, we just give them a I'm Not a Robot direct pass to.
That's really
so
good.
Yeah.
What was the most significant challenge you ran into when creating the reCAPTCHA?
Oh, there's many different challenges in there, right? So first of all is, look like a black magic, right? What happens behind the scene that made us feel confident that you are robots, you are human, not robot. So that we had extensive kind of a collaboration with the security community inside Google. So if you think about today, right, you go somewhere and you say, oh, I want to log in. And you'll find out, just having your password is not enough. You have a user where you have a password, and then they will pop out and say, oh, what is your phone number? Let me send you a SMS, right? Something like that. So turns out that, among the security community at that time, they already practiced this kind of risk-based system. So based on various signals that you give, right? So including your password, including, your browser and various things that you use, through your HTTP request to the server, they can tell a lot about, this particular user, right? So based on those signals, we can do a pre-classification, and we're confident, we let you pass directly. So that itself is a technical challenge. There's also a business challenge in there. So at the time when I took over that team, even though it's still widely used over the internet, but it's one of the most hated products over the internet, in the sense of, people don't like to see those distorted text, which made them guess and only get them correct 33% of the time. Right? So the user acceptance at that time, and there's actually a activist group inside Australia. I think it's called Australia Consumer Activist Group, and they challenged and advocated for a lot of websites to drop this solution because it's extremely painful for people with vision impaired users. Because first of all, they cannot see this very well, and if they listen to the CAPTCHA, we actually give them very distorted voice CAPTCHA, right? So it made it extremely hard for them to pass. So that was the time when I took over the team. There's both business challenge and on the technical side, it's not very clear how do we pivot this. I think the biggest lesson I learned from there is really being open about what you're trying to do and ask for help. Right? So there's a lot of very smart engineers inside Google in the larger communities reaching out and form collaborations. And a lot of times I would say to my team is, if you open doors for others, they open doors for you as well. So that was the biggest thing I learned in there.
Great, thank you so much for sharing your journey in redesigning reCAPTCHA. So we also have a question from Ira in the chat. She says, what do you think about people concerned about self-driving cars? Do you think their fears surrounding the tech are justified?
Oh, definitely. I myself, right, if I sit through, I think, 2 different self-driving cars by 2 different vendors, and I clearly see how, I'm first impressed by how advanced the tech is. Second of all, we are not ready yet. So I wouldn't sit in any, a car that doesn't have a driver today. But we're talking about a decade from now, and it took time for humans to accept this as well. So my best analogy is you look at 100 years ago, right, when car was a new thing at that time. I think I saw a picture where in 1911 or something, on a busy street of New York, where most of the carriage is pulled by horses, and there's one automobile in there. And then a decade later, most of the carriages is actually automated automobile, but there's one horse carriage in there. So that's just how things change in one decade. So don't underestimate how humans are adaptive to the changes in the world. Right? So I think in terms of getting us into self-driving car, there's at least two different, maybe three things that we all have to work on as a society. So as STEM or engineers or researchers, improve the tech. Spend a lot of time investment in technology, getting us in there. Now on the other side is general public and policymakers. Right? I think California did something especially well, is giving license to the self-driving companies who want to try in the public roads, and ask them to report the metrics. So one of the metrics that we use is called MPI. This miles per intervention, how many miles you can drive without a human, take it over. Right? And of course, the longer, the better. But having, this mechanism, having different, companies report where they are, it really give us, as general public, more confidence of, seeing the advance of the tech in there. Right? So in essence, it's a policymaker, make, the testing, given the testing permit, so allow the companies to try it out, right? And the general public is, having kind of observing. I'd be interested in the topic, observing the advances in there, and kind of be more open-minded about this. And I think it all take time. Another decade, my guess is it won't be rare for us to see a car that's totally self-driving in limited condition. I'm not talking about everywhere in the world, because that still take probably several decades to get in there. But in limited condition, in the sense of, for example, even today in Arizona, I think it's outside of Phoenix. There's few companies trying it out, because the weather is it's all sunny days, wide roads, few pedestrians. So make it a lot easier to pilot your program, your self-driving program in there. So as we see progress in there, right? So you can get to see maybe in highway, that's another condition that's much easier to try out, just because you don't encounter a lot of uncertainties in there. It's just cars, right? You don't have bicycles and pedestrians in there. So I do think highway is another possible area. And after that, probably some of the kind of easy suburban areas that you can start seeing self-driving cars. And then probably several decades later, the most difficult places, one is in downtown, right? Because there's many things could happen in there, many unexpected unknowns. Other places would be, extreme weathers, right? Drive in snow when the whole ground is, covered by ice, right? What do you do? Probably even it's a challenge for human driver today.
Definitely. So Ella Liu also has a question about the gender bias in STEM. She asks, are there many females in your department?
We're getting better. I actually have, spent some time looking at the stats. So the thing that we're seeing is in grade schools, usually, you're saying, boys and girls, 50-50. In college, in engineering majors, it has a drop into 30% of girls. And when you come to the tech industry in Silicon Valley, the ballpark number is in engineering technology departments, ballpark number is 15%. Right? So we already see like a 50% drop from college into industry. Now, as that further grows into management, senior management, so we're looking at probably 5 to 10 years, after you started, working. the woman that's holding some senior management role dropping to 5%. So that's just the facts of the data, right? But it's very interesting to look into why, what made all these changes. And a lot of times, I've seen what the industry is doing. We created a mentorship program where we pair, senior women with, more junior, entry level female engineers, and to guide them through the career development. So that's one thing. Another thing that we want to look more into is, further into college or even into high school, right? Having a lot more girls interested in this field is definitely something that we want to do more. And that's really one thing that motivated me, right, drives me to come in here and talk to, the rest of the youth here. It's just to show that, there are women like us in there, right, still working in the STEM field and, trying to make a change in the world. And your career can, grow very long.
Yes, I think it's great that you guys recognize the problem of this decrease in the women in STEM, and then even started a program to pair the seniors with the freshmen. I think that's great.
Mm-hmm.
So another question is, during your time at Google, you worked with Google Street View in assembling what's called a labeled data set. So could you talk a little bit about?
Okay. So the particular team I am running is called a data platform for AI. So what it does is, when you're training an AI system, right, there's several ways of doing that. So one, the most popular one, a well-established one, is called supervised learning. It's actually mimicking, from how human learns. Supervised learning, as human, you'll be thinking about, sitting in a classroom where your teacher, write it down, this is how things works. And, you remember them and trying to apply them into your, taking tasks in your real world. So that's called, somebody teaching you. So that's the supervised learning part of that. And turns out, in training an AI system, we do the same thing, right? So given a concrete example is, I mentioned about we collecting a lot of imageries from the street view. And then we have human, first pass is we have human to take a look at the image and kind of drawing bounding boxes around, street signs, street names, and then transcribe, right? So this is 1, 2, 3, and this is Main Street. So this is making what we call unstructured data, an image, into structured data, which is, you can put it into a tabular form, right? So a table and say, image 1, it has 1, 2, 3, Main Street. So using this structured and unstructured data, we feed it into an AI system. So how AI does is, it's learning from your input, which is a pair, the input of the imagery and the expected output, which is unstructured data, 1, 2, 3 Main Street. You're trying to figure out the pattern around them, right? So the logic from, mapping the input into the output. So if you feed enough of this data into there, then, in our case, we actually have a billion annotated data set into the system. So the system will learn this logic and then becoming what we call a model. The model is essentially, the pattern between input and output. So once you have the model, you can deploy it somewhere, and then you can feed into, feed it with another unknown picture. And then the model will try to figure out, oh, in this picture, I actually see, A street in there. Right. So that's how, in a very high level, how the, machine learning system works. So in order to get there, you need a lot of input and output, expected output. That's what we call the labeled data set. So my particular team is to do this, creating a data platform so that, on one side we have petabytes of imagery come in. We chop it down into individual frames. We feed it into many what we call annotators sitting, in front of the computer, given a picture, they draw a bounding box, they annotate it, and then it becomes the structured data. So my team is taking care of this end-to-end data flow. So becoming structured data and then feed into the Google Brain system.
Oh, thank you so much for talking about that. I don't think a lot of us know about that. So we have our last question is, what is one piece of advice you would give to female students aspiring to become leaders in the STEM field?
Mm. So I think there's kind of three different concepts in there. There's like first the female student, second is leader, and the third is in the STEM field, right? A lot of times, if I try to decompose into different dimensions, I find it very hard to think about what the right thing to do in there. So instead, my approach is make it simple and just think about what do you want to do and what's preventing you from doing that. So my general, if I summarize into one sentence, is just do it. This is the Nike's logo. Just do it. If you find something you're really passionate about and you want to learn a bit more, being curious and find out how you can learn and become better, and just do that thing.
All right, thank you so much. So we all really enjoyed your speech, and we thank you for your time. So next, I will pass this to I will pass this to Marissa, who will introduce our next speaker. Thank you so much.
I have the great pleasure of introducing Dr. Anna Doblas as today's final speaker. Dr. Doblas received her PhD degree in physics from the University of Valencia in Spain with the highest qualification, and her work was awarded with the International Mention. Currently, Dr. Doblas is a research assistant professor in the Department of Electrical Engineering and Computer Engineering at the University of Memphis. Her main research interests include 3D optical microscopy and image formation theory. Please join me in welcoming Dr. Doblas.
Can you hear me?
Yes, we can hear you.
Thank you so much. I'm gonna share my screen, okay? Can you see the screen?
Yes, we can see your screen.
All right, so let me kind of talk about what math has been important in my professional career and what it means to me. First of all, so I don't know if you know where is Spain, but this is this tiny country. And I was born around really close to the Mediterranean Sea. My parents were immigrants from the south of Spain, and none of them never had a bachelor degree, and neither a PhD. So they moved to the south, to the East Coast, to kind of find a better opportunity for them, and kind of a better opportunity for their children. Of course, was around the 70s in Spain, a Catholic country, so girls need to stay at home, raise their kids, and this is not the mentality that we have right now, but this is the mentality that my mom needed to break. So my mom kind of raised us, to my brother and myself, say, you do whatever you want, try to follow your dreams. And I joined a Catholic school, and my first feelings about math were horrible. Completely. In elementary and middle school, I didn't like math. I just kept memorizing the problems. My brother is 8 years older than me, so everything that I was doing, I was always behind him. So he was really good in math. And I didn't know how to do it, so I was really good memorizing and on letters. So what I did was, okay, so let's memorize the problem. The professor was kind of lazy. So most of the time, the problem for the exam was the same. So my grades were good, but if the problem slightly changed and I was not able to pick up the pattern different, I could fail the exam. So I was so stressed about the math, and I thought okay, in the moment that I'm gonna start the upper level of middle school and high school, I will move to the letter side. But I moved to middle school and there were two new professors. The two ones, so he is from the telecommunications engineer, and she is from the mathematical background completely. And the way that they introduced math to me, it was completely a new world. I remember discovering, hey, I understand this. Math is important. I know how to do it better. And I was always more interested about math. Maria Jose, who is the director of the school right now, she started to create a club. So we were going to compete outside in a math competition, and that was really something to me. Like we were staying after the class to just do more problems. And she made us to have different levels of math within the class. So she was completely, the class was not specific to a person. It was not specific for the whole class, different levels. So she was giving different math levels within the same class at the same moment. And when I was 13 years old, my brother was almost finishing his degree in math. So I'm 8 years younger than him. He has been always my hero. But by that time, the age gap, it was huge, and I was never be able to play with him. But math was something that somehow connected us. So talking about math, I really worked closer to my brother. And when he finished his math bachelor degree, he joined the PhD program. And he was able to more stay at home with us making research. And I was really see, like, she was showing me all his research. And I was the moment like, I want to have a PhD. Like, that's something that I want to do. I don't know about what, but I just want to have my PhD degree as my brother will do it. So by the end, so math is what you study in the beginning of the middle school, but math goes back later with physics and chemistry. And I was kind of like, I don't know what to do. Like, I really like physics and I love it, chemistry. So these three subjects become competing always, like what I'm gonna do, like in which part I'm gonna be best. And by that time, my sister-in-law, which was the girlfriend of my brother, she is also a mathematician. So I was kind of thinking like, two math people in the same family, like I need to break it. I need to do something different. And by the end of the high school, my brother and I would discuss a lot about which degree. So he didn't regret, but he always felt like you need to do an applied degree, like some engineering. So he was always trying to convince me, go to college telecommunications engineer. But I didn't want to do that. I wanted to study the foundation of the math or the physics. Like before solving a problem, I need to understand the problem. So for me, engineering, it was not what I wanted. I wanted to go down. So we were discussing a lot and he was telling me, sure, I get what you want to do, but if you follow math or physics, maybe you're just gonna finish in a different place that you don't want to be in the future. So we discussed a lot of time. I didn't follow his advice totally in the moment because I definitely joined physics degree. So in Valencia, where there is the science campus, the STEM campus, there are physics and the building in front of physics faculty is math. So I just joined the physics department in 2005, which was the year of the Einstein, which was a great year to start physics. And I just did my bachelor degree in physics. So it was kind of like, for me, it was kind of easy. I always stay in academia. I have been so lucky and always going to scholarships and at the end, a postdoctoral position within the academia. But within the academia, when I joined the physics department, my first thing that I had in mind, I want to be Einstein. I want to study nuclear physics. I want to work in the CERN, or I want to work in NASA. But this whole idea, it completely changed. So in 2008, after my first 3 years of the bachelor degree, we needed to choose a specific concentration of the physics degree. And I thought, okay, let's go to NASA. Let me see what I need to study if I want to finish in NASA. So that was methodology and atmospheric physics. And I talked a lot with the professors in that field. And they told me that the opportunities afterwards, there were few. And of course, if there are few, they're gonna go for the best universities. So that was not a future or a long-term future for me. And I talked again with my brother, and my brother said, go to applied physics, go to a degree, a concentration that's gonna give you the access to engineering. So where there is engineering, there is always money because you're gonna solve real problems. And I joined the applied physics and photonics. So photonics is optics. And in high school, you already learn a little about optics and how the lens is gonna work. And I remember that I really like it. So I thought like, okay, that makes sense. So I joined applied physics and photonics. And before I finished my bachelor degree, I already had an offer to do my master and my PhD with a group. But that was the moment where I had two offers. I have an offer for the telecommunications engineering department, and I have an offer for photonic systems. Both fields, I love them back on the day, and I wasn't sure which one to go. This one, make sure that to have a lot of future because it was completely novel. But for the photonic systems, but there was not a lot of experimental things. There were more like simulations stuff. But in photonic systems, they allow me to derive theory, have the simulation, and prove it experimentally. So I have like the three topics that I like the most. And I did an internship over the summer. And I really enjoy the atmosphere, the environment of the research group. So it was clear to me, like when I finished my bachelor degree, I'm just gonna stay to the photonics topic. And I joined the 3D imaging and display laboratory at the University of Valencia. So what we do there is, what we do is we try to develop new microscopes. So when you have in mind a microscope, this is the picture that you usually have, right? So that's where biologists are gonna see different samples and tissues to kind of detect if there is a cancer cell or how the motility of the cancer cell is changing to figure out if the drug is working or not. But before to having this nice commercial system, you need to develop. And how you develop is completely a Lego game. So you have all these plays that you need to put together until you have this huge microscope that when you test it and you verify the performance later on the technology development, you're gonna make everything so tiny to fit it and make it nice and done. But this is where completely I do. This is a commercial system. This is a prototype of a system that is commercially available only for 2 different companies, and it's slightly different, but this is occupy a whole table, and when the university is open, you are welcome to reach me and we can go to the lab, but this is exactly what I do. So where are the math are playing a role here? So everything for the optical system, it's mathematical knowledge. And the math make a lot of sense because how is the response of the system, the final image that you're gonna get through a microscope, this is expressed in terms of a mathematical equation. And and this is the image, or this is the simulation of how a unique point on the object is gonna get image. And just these three images, which are in different focus plane, this is completely this huge integral to be solved. So mathematical knowledge in physics is huge. And if you have it, you're gonna make for sure if your system is behaving as is expected, because that's a key point. You need to, and a lot of time for designing new systems, what you need to go back is to the foundation of the math. Like, what is the drawback that I'm having? How I can fix it? And a lot of time, how you can fix it is, oh, if that function is different, then the result might be different. So then you have the following question: how experimentally I can change that function? And you keep laying out all the layers of the complexity until at the end you have a completely experimental system that when you test it, you always compare your final results with your theoretical expectation to make sure if it is what you were expecting or it's not. And ideally, if everything has worked out really nicely and there is no mistake, your final experimental system needs to be predicted by the theory behind. And more projects that I'm involved in right now is, so when we have our blood is composed by different components. We have red blood cells, and we have 5 different types of white blood cells, and we have platelets. So how healthy you are, or if you have some disease, you can be able to detect that disease just looking at the red blood cells. So the normal red blood cell is completely biconvex, and the refractive index theoretically, but it's like, imagine like a donut without the hole. But if you have sickle cell anemia, for example, you're gonna have like the crested moon shape. Or if you have iron deficiency, you're gonna have like a cell like looks like a pencil. So be able to image red blood cells, it's gonna give us an idea about how healthy you are. And for that, we need to have an imaging system that is accurate. The resolution is really nice, so we can make sure that we are able to screen all these different type of red blood cells, and it's fast. And ideally, it's label-free. We don't want to stain the samples. We don't want to add toxicity. We just want to put a smear of red blood cells and get the images through them. So what we did with the red blood cells was make the difference between the red blood cell from healthy people and people that they were afflicted with diabetes type 1. So these are completely experimental images of a microscope that we built in Valencia. You're gonna see that the colors are pointing out different values of the phase. And the phase here, what they mean is how much time it gets trouble the light to get through the image. And the phase value, it's higher for the diabetic people than from the healthy. And in fact, when we were going through the statistical analysis, we realized that if the value of the phase was higher than 4, all the people were, well, not 4, 3.4, all the people were diabetes. So what is the next step? We prove that a microscope, looking at the red blood cell, we can differentiate between diabetes and healthy people. So the next step is, I don't want to do the processing of the imaging. I'm just gonna use AI to tell me if you have the value of the phase, tell me what is the value for the doctors that are gonna use it. So the doctors use the glycated hemoglobin, which you need to fast and you need to extract a lot of blood. So the idea, like, if this is only a single drop of blood, I can diagnose the phase. Can the phase give me the glycated hemoglobin value in a much simpler way? And the first thing that we did was, instead of trying a lot of algorithms, we just try a linear regression algorithm from the face value to tell us what is the glycated hemoglobin. So again, this linear regression is mathematical there. So math, it's everywhere. You might not realize, but it's everywhere. And that is why math is important to me. And hopefully I can convince you about follow your dreams if you like it.
All right,
Happy to answer any question. Yeah.
All right, thank you so much for your time and giving us that speech. We really enjoyed it. So next, we will go right into the award ceremony. So, all right. 1 second. Okay, thank you so much, Dr. Doblas.
No problem, thank you.
So for 5th and 6th grade, for top 3, we have Sophia Henningsen from Fallon Middle School, Ava Chin from Miller Middle School, and Cynthia Hu from Cabrillo Middle School. Congratulations to you guys. And then for 7th grade, our top 3 winners, we have Ashley Huang from Miller Middle School, Ellen Lee from Fowler Middle School, and Audrey Perry from Harmony Science Academy. So congratulations. And then last, we have grade 8, top 3 winners as Vivian Law from Winchester Thurston School, Nancy Lay from Basis Independent Fremont, and Gracelyn Hall. Congratulations to you guys once again, and we have one last top 6 overall winners. So we have Nancy Lay in 6th place. 4th place and 5th place, we had a tie between Vivian and Sophia. So congratulations to you two. 3rd place, Audrey Perry. 2nd place, Ellen Lee. And 1st place, Ashley Huang. So congratulations to everyone who attended. And we are so happy that you joined us this year. Hopefully next year we will be able to host our MIG competition in person, but we can only hope for the best. So we hope to see you guys there. All right, thank you so much. Congratulations to everybody.
So to end this Zoom meeting, I forgot to introduce myself at the beginning. My name is Valana Wang, and I was a president of MIG this past year. And just to give like a quick little thank you and to all of our participants and also to my team. As we all know, I'm sure the situation with the virus this year has definitely impacted our lives in so many different ways, and it forced us to transition. It forced us to think on our feet really fast. This is the first time MIG has ever encountered a problem as big as this, and we had to transition online. And I am so happy that we had such a great turnout and that all of you guys were still interested in joining our competition. And in addition, because we moved the competition online, we were able to get students from outside of just our region in general, and we were able to welcome several of our participants from outside of this region, which I think was a wonderful opportunity. So I think that one thing that we can definitely all learn from this year is that we really never know what's going to happen in the future. I'm sure that the virus impacted all of your lives in very big ways. It certainly has impacted mine. I'm going off to college next year, and it will definitely like be a transition. But even in the most unexpected situations, I think that there's always something positive that can come out of it, and there's always something to be learned. So I actually really value this experience. We had, I would say, nearly 100 participants. I think somewhere 80 to 90 participants we had this year. So I think that this was just a wonderful opportunity, and I'm so glad to everybody that participated. And I just really want to thank my team for going through all of this with me and putting up with everything, even when the virus hit. So thank you to everyone who participated. We will be sending out each of your scores individually to your emails, so be on the lookout for that. And if you have any more questions, you can always email us at our Gmail account, mathinviteforgirls@gmail.com. So thank you again to everyone, and thank you to all of our speakers. Once again, it was such a wonderful opportunity to hear all of your speeches and have all the Q&A sessions.